going to talk about dilutions in just a minute, but I wanted to talk to you first about something kind of related, and that's the science of homeopathy. So let's watch this video.
What you do not smell is called iocane powder. It is odorless, tasteless, dissolves instantly in liquid, and is among the more deadly poisons known to man. All right. Where is the poison?
What in the world can that be?
What? Where? I don't see anything.
Let's drink. Me from my glass, and you from yours. You fell victim to one of the classic blunders. Never go in against a Sicilian when death is on the line.
Think. All that time it was your cup that was poisoned.
They were both poisoned. I spent the last few years building up an immunity to iocane powder.
So here's a homeopathy treatment that you can buy on Amazon. Whatever this stuff is, I actually had to look it up, and it turns out that it's just carbon monoxide. Carbon monoxide is a gas, right? So you'd think about this being a dissolved gas, like fizzy pop or something like that, right? Now, why is that important? Well, carbon monoxide is something that's quite dangerous to your system. If you breathe in too much of it, it binds to your blood carrying molecules, it binds to the heme, and it basically displaces oxygen. So too much carbon monoxide is poisonous. It suffocates you. So how would that be a treatment for anything? Well, let's think about, I don't know, a virus, a pandemic, and the fact that you get this virus and you can't breathe. So maybe this stuff is supposed to open up the lungs or something. I don't know. But let's talk about this 30CH. So that's a denotation that signifies the concentration, in a way, of the carbon monoxide. The C is Roman numeral C, so that means 100. I actually don't know what the H is. It's a 30C dilution, which actually means you take your sample, dilute it 100-fold, and then dilute that again and again and again 30 times. Is that a small number? Well, yeah, it is. This is what the number works out to be. Yeah, whatever that is, a very, very small number. It doesn't quite make sense. So let me just give you an analogy to sort of get a sense of what this number actually amounts to. So let's begin with a single drop of water. Now that drop of water would have to say would be saturated with carbon monoxide. Now we got to dilute that. So we take this drop of water and we throw it into the world's ocean. Now we got to mix that up to make sure that the drop is properly distributed, so the carbon monoxide is stirred around inside of the world. But we're not done yet. Now what we're going to do is we're going to take one drop of that, drop it into another world's ocean, and stir that around, okay? So if you took that water and put it in a bottle, you would actually have stuff that's like thousands of times more concentrated than this stuff right here. You want to buy this stuff, just go like this. Just breathe the air. You're going to bring in way more carbon monoxide than that. This is like pure water. There's nothing in it. There's just water. Even if it had carbon monoxide, it's not going to do anything. So like, figure this stuff out. This is not science. This is not a treatment. This is just dilutions gone haywire. Okay, if you do want to protect yourself from the pandemic, put a mask on, please, and everything is going to be fine. So we're calm, I'm good. There's going to be a lot going on in this video. We're going to describe making solutions in a kind of a complicated way. So let's get down to business. Okay, take this off. Okay, in the last video, we talked about concentration. The usual grams per mole, you got the ppm, the weight by weight percent. There's just one more little concentration thing that I want to throw out there. Just a quick, this is a definition, very, very quick. So let's take the situation here. We're going to dissolve 35 grams of salt into a liter of water. We're going to ask, what's the concentration? So just to give you a perspective of what we're talking about here, 35 grams is a couple tablespoons dissolved into a liter. So we're making salt water, right? The saltiness of that water is about the same as the saltiness of the ocean. So the question that we're after here is, what is the concentration of sodium chloride? And here we're going to talk about molarity. Okay, so what is the moles per liter of sodium chloride in that solution? So for a problem like this, you got 35 grams, we've got to calculate the number of moles. So we'll do that conversion over here, 35 grams divided by the molecular weight. And you'll see in here that the masses will cancel out. The units will be left over as moles, so about 0.6 moles per liter sodium chloride. It seems okay, nothing wrong with that. But actually, there's completely something wrong with that. This is not the answer. The question is, what's the concentration of sodium chloride in that liter of water? But let's think about the chemistry that's going on. You take sodium chloride, you dissolve it in water, and this is what happened. It dissociates into sodium ions and chloride ions. The concentration of sodium chloride did start off at 0.6 moles, but by the time it's dissolved away, there isn't any of that left. So what do you need to do? Well, you just make up a new word. It's not that we don't have 0.6 moles of sodium chloride, it's just that we don't have it in the solution. So instead we talk about formality. That's the word. It's like molarity. It just ignores the fact that the sodium chloride has actually dissolved away. So the concentration is 0.6 moles per liter. We're just putting a technicality on it. All right, we'll just leave that definition there for now. You can read it up in your textbook if you want to know a little bit more. So we did this problem in a previous video, but let's just go through this very quickly again. Let's say you got 35 grams of sodium chloride. We want the weight percent of sodium, realizing that all of our sodium chloride is not pure sodium. So we have to kind of account for the ratio of sodium relative to the total mass. So how do we calculate the mass of sodium? Well, we need a relationship. So to go from sodium chloride to sodium, you need to have this ratio. So basically look at the units. You can cancel them right out. If we have 1 mole of sodium chloride, we have 1 mole of sodium. And rather than writing down in moles, let's write down in masses, because we are thinking 1 mole. And I can take those numbers and express that in my ratio instead. And notice the units. Everything is canceling out as we want it to be. So from there, we calculate the mass of sodium compared to the total mass of sodium chloride. Okay, the problem isn't quite done because we're trying to calculate a weight percent, so the mass of sodium divided by the mass of the solution. So I said in the previous video that the density of water is about 1, but this isn't really pure water. It's like pretty salty water. It's ocean water. Its density is a little bit different. So how will that change? Well, we could say for now that the density is 1, roughly. So a liter is going to be about 1,000 grams. But if you were to look this up, or in other words, if I were to give you this problem in a question, we could find the density of our ocean water, and we'd see that the density would be 1.03. So in fact, the mass is not 1,000 grams. The mass is just using the density 1,030 grams. So I'm just going to put that number into the expression, and I'll calculate the mass ratio from here. And this is expressed as a fraction. Now, just to sort of move the decimal places over, I could multiply that by 1,000,000. That would express this concentration in parts per million. Because this is a reasonably big number, I'll multiply by 100, which will move the decimal place over by 2, and I'll get 1.3%. All right, now we're going to talk about dilutions. So this is probably a familiar problem to you. However, we'll go through it. So let's say we have a solution, and it's given to us with a certain concentration. So C1. You could also say that's the initial concentration, so C sub I. Now what we're going to do is dilute that concentration by taking a certain volume of that out. You usually would use like a pipette or a graduated cylinder, so we know exactly what volume we're stealing from this solution. The concentration in here will of course be the same as the concentration that we started with. So what's next? Well, we take the exact volume that we have and we deposit it into a new volume. So here it happens to be a 1 liter flask. So I'll pour that in, and then we're going to fill that up to the mark just with water. So there's going to be a new concentration here. We'll call it C2 or C final, that depends on what we started with as well as the volume that we moved along. So we've got a bunch of terms in this expression. We have C1, V1, we have C2 and V2. So what's the relationship that holds in all of this? Well, we have to think that the moles that we have in this container is equal to the moles that we have in that container. And I said moles, but it could be any unit. So the mass of whatever analyte is in here has to be the same as the mass of the analyte. I'm not talking about the mass of the solution. I'm talking about the stuff that's dissolved within it. So the expression C1V1 equals C2V2 just relates the moles in the initial solution to the moles in the final. And we're actually talking about the moles in that small container as we dilute it through. And usually, because the question is, what is the concentration of the second solution, you can just take the equation and rearrange it. Personally, I like this version of the equation a little bit better because what you're looking at here is the concentration multiplied by a ratio of volumes. This is our dilution factor that you're thinking about. Yeah, it's the same. I've just rearranged one equation from the other. But just for me, mentally, this is kind of how I think about it. So let's take an example. We'll take 1 molar HCl, 10 mils of that, and we're going to dilute it to 1 liter. So the question is, what is the concentration of HCl once we've diluted it? So really what you have to do is just organize the information. We have these 4 terms, C1V1 and C2V2. There's a lot of numbers given to us in the problem, but as long as we can organize where they are, this is pretty straightforward. Take all those numbers and rearrange into whatever version of the equation you prefer and solve for the unknown. So you can see when I put the numbers into the equation that the volumes cancel out. Now you might not be used to doing the problem this way. Perhaps you would prefer to take your 10 mils and express that as liters and your 1,000 mils as liters as well. Honestly, as long as the volumes are the same, they are going to cancel out. So just do whatever you want to, just make sure that you're seeing these units disappear. And I do always recommend that you actually write down your units in these expressions, so we're not just talking about this arbitrary 10 and 1,001. I'm always writing units down to help guide what it is that I'm actually working on. All right, so just to finish things off, I just do the calculation, and we end up with 0.01 molar, and if you prefer, 10 millimolar. That's our final concentration. This is a very similar problem. You're given similar information. You're just being asked to calculate a different variable of that same equation. So the key to most of these problems is really organizing the information. You've got variables to work with, the C1, V1, C2, V2, and you've got the question. All you got to really do is make sure that you're sorting out which number falls into which of these variables. Once you've got that, the problem is really just plug and chug if you do this right. So make sure you know which volume that you're dealing with. All right, so let's just continue this expression anyways. We've got a bunch of numbers that we know, and we have one that we don't. So let's just plug them in and see where we get. So the numbers from the question plug in here, and we rearrange, and we solve for V1. V1 works out to be 25 mils. And again, notice that I didn't actually convert 250 mils into 0.25 liters. You can, there's nothing wrong with that. It's just your final answer will be expressed in liters as well. But one thing that did matter here is that the 0.1 molar or 100 millimolar had to switch over. So the issue with that is that if this side had molarity and this side over here had millimoles, the two wouldn't work out. So you do have to bring them together in a common unit. So really the key to this question is not in the plug and chug, the algebra. I'll call that pretty straightforward. The key to getting these problems right is to be able to define the variables of the question. To do that right, for me, it always involves drawing a picture. And you see that I'm not scratching out with the beautiful artistry. It's just putting simple diagrams together so you can label things accordingly. This just helps me to visualize what it is that we're actually doing with the problem. So this is like a different kind of problem. And I say different because it's one that doesn't even necessarily have an answer, or certainly not one answer. So here's a calculation that there's more than one way to do it. And I guess there's one way that's more correct than the other. Anyways, let's see where it's going. What we're going to be asked to do is make up these samples. Okay, now we're not doing it in the lab, but before you go into the lab and say, let's make up these solutions, you do have to have a plan. So let's put numbers on it and say, this is our goal. We want to make this whole range, starting off at very high concentrations and working our way down to very low with a few in between. I did mention this in a previous video, and the volumes that we're working with are the ones that are shown in the picture right here. Now, believe it or not, this problem is really down to C1V1 equals C2V2. It's just going to be done many, many times because we have multiple volumes, multiple concentrations. So you could think of them one at a time. But which one do you think about first? Like where do we go? We know that our goal is to make up those solutions, but there's really more than one way to get there. You can choose a different path. So this is almost arbitrary thinking, but what I'm going to think here is that first solution over there, the most concentrated one, can actually be used to make all of the subsequent solutions. They're all just dilutions of our 1000 ppm sample. So if I call the first concentration C1 equal to 1000 ppm, I can use that to calculate all of the other numbers. Because I'm given the volumes, I'm given the concentrations. So it's just a matter of rearranging this equation. Now, if we do that, we'll come up with the volumes that you see in the table over here. So, for example, if I want to make 50 mils of a 100 ppm, it's a 10-fold dilution. So it makes sense that I'm using 1/10 of the volume. 5 mils dilutes into 50, and there you go. I've got that 100. Now, some of these have different volumes, but the equation is still the same, the way that you do the calculation. So we can calculate all of the volumes working your way down. And you're done. Nothing wrong with that. Or is there? Well, the way I see it, you've sort of picked a path that leads you into a little bit of a trouble. And what is the problem? Well, all I've done is the same numbers, but I'm just converting units. So we got mils and microliters working our way down the line. Is it reasonable? Your calculation's right, but is it reasonable in person, in the lab, to actually do this experiment, to move these volumes around? Can I pipette 5 mils? Sure. A half a mil? Yeah, we got pipettes on that. These volumes are getting small, really small. We actually do have simple instrumentation that allows us to accurately deliver volumes like this. And usually it would look like one of these. So this is a micropipette. You can buy micropipettes that will accurately deliver volumes down to about 1 microliter. But once you get to volumes like this, a half a microliter, maybe, but 50 nanoliters is such a ridiculously small volume. Unless you've got really specialized equipment, this is just not a practical thing to do. So to roughly divide out these numbers, you could see that some of the concentrations give you reasonably high volumes to work with. As we work our way down, we have medium volumes, which they're still doable as long as you have the right equipment. At the low end, there's just nothing practical that we can do in the lab to deliver volumes of that nature. So while our calculation was correct, the practicality of the solution just leaves the whole thing in question. So this is a slightly different approach. It's still simple, it's still practical, it can be done in the lab quite quickly. And the idea is to do a serial dilution. So if we start with our initial concentration, draw up a certain volume with a pipette, and make our new stock. We can mix that up and then repeat the process where we draw out another volume and dilute it down one more time. So let's just put some numbers down here. Let's say that our initial concentration is 1000 ppm and the volume of the pipette is 10 mils. The final volume that we're diluting into is 100 mils. So if I just want to calculate the concentration of the middle solution, I can use the numbers that we're reporting here. And as I said, I like to deal with dilution factors. So if we take our 1000 ppm and multiply it by 10 on 100, we get to our new concentration, 100 ppm. And likewise, you can apply the exact same logic to go from 100 ppm to step down to 10. So I know this might seem a lot more complicated, at least mathematically, but practically it is a lot simpler way to get to the solutions that we need. What I'm doing here is I'm dividing up my solutions into different ranges. And I'm recognizing first that to go from 1000 to 100 to 10, the first 3 solutions on our table, all I need to do is this 10-fold dilution. So a serial dilution of 10 mils into 100 mils provides me with 100 ppm. I do that one more time and I can quickly get to 10 ppm. Now if I use the 10 ppm solution as my starting point, I can use that to dilute all of the samples in the middle. So to get 8 ppm, I'm just going to take 8 mils and dilute it into 10. To get 6 ppm, I just take 6 mils of my stock, dilute it into 10. You see where this is going. And finally, as I work to the very low concentrations, you again see factors of 10 in the dilution. So I can take that serial dilution, beginning with 1 ppm, dilute it by 10 to get 0.1, dilute that by 10, and dilute that by 10 again. So the trick here is that the concentrations that we start with actually change. Instead of starting with a constant value and trying to dilute that down to an insane level, we're going to do serial dilutions. I've decided what these numbers are going to be. Does that mean that this is the only right answer? Not even close. The previous one was a correct answer. It just was an impractical one. So, I bet you didn't think that that simple equation could get this complicated. And yeah, I'll admit, this is complicated stuff. So how do you go about it? How do you navigate this stuff? Well, you do your problems, okay? Like, we've got problems like this in the book for you to work on. The weird thing is that there isn't necessarily one single correct answer. And one of the other things that I showed you in this video is that you really have to start organizing the information, okay? The most important thing is to understand your variables, to put clear labels on them. And I even went a step further and say, why don't you draw some pictures? Any way that you want to organize the information, table form, picture form, but just make sure that you're keeping everything on track. So once you do that, working with problems of this nature should start to get, I hope, a little bit easier. You got to do your practice, so we'll see you at the next video.